Hello everyone, welcome once again to another tutorial session in bioinformatics. In today's video, I am going to show you how you can use machine learning to predict diseases. This tutorial will follow the outline I am displaying right now. I will first give a brief introduction about the disease of interest for this tutorial, and then I'll also state the PC requirements and give the motivation for this video, as well as the reference article from which this tutorial was prepared. We will then move on to the machine learning task itself. So let's begin. The disease of interest for this tutorial is malaria. Malaria is a serious disease that is caused by the Plasmodium parasites. This parasite is transmitted to humans through the bite of an infected female Anopheles mosquito. Malaria is a major global health issue, and it affects thousands of people each year, and a lot of deaths occur as a result of the disease. And there's a lot of research going on to develop intervention measures for this disease. And so I also thought of making this video so that I'll show people how technology is being used to fight this disease. I am going to use hematological data for this exercise. Hematological data is blood measurement and includes the measurement of hemoglobin levels, the count of red blood cells, white blood cells, and platelets. I will demonstrate the machine learning work using the random forest classifier. In order to follow this tutorial, you need to have Python installed on your system. And you also need to have the following Python libraries installed: NumPy, SciPy, Pandas. These three will be used for data handling and manipulation. Matplotlib and Seaborn will be used for data visualization. Scikit-learn will be used for the classification task. You can install the Python libraries using the pip command, and I have videos that shows how to do this. The links are in the description box, so please watch them. This tutorial is based on a reference article that I am displaying right now. In this article, the authors use machine learning approaches to classify different malaria outcomes. And this is how a machine learning work should be. It should be about solving problems. And so, if you are working on a machine learning project, one of your aims or goals should be to solve a problem, and the problem should be relevant. And so, in this article, the authors try to solve a problem related to malaria diagnosis. Methods for diagnosing malaria include microscopy and rapid diagnostic tests. But these methods have their own challenges. One of the challenges is that microscopy diagnosis is subjective. So from the preparation of the slides to the interpretation of the slides, all these depend on a person who is performing the task. If you take a look at preparation of slides, we can have what you call staining variability. And this is where the amount of stain used or even the staining procedure differ from person to person. And this might affect the viewing of the slides and the interpretation of the slides as well. Rapid diagnostic tests are also faced with the challenge of false negatives. And there are a number of reasons why we can have false negatives. And one of them is the deletion of the PFHIP2 and 3 genes. Now, PFHIP2 and 3 are proteins that are found in the Plasmodium parasites. And this is what the RDTs use to detect the parasites in the blood. But over time, some of these parasites have evolved to not have the proteins being expressed in their genomes, and therefore the RDTs are unable to pick these parasites up, even though they may be in the blood. There is also the issue of misdiagnosis that occur as a result of low parasitemia. Low parasitemia is a situation where we have low numbers of parasites in the blood, and therefore there's a challenge of using microscopy and RDTs to detect the parasites. There is therefore the need to develop alternative methods for diagnosing malaria, and this is where the paper comes in. So in this paper, the authors propose an alternative method for diagnosing malaria, and they used machine learning approaches. The dataset that was used for this study is publicly available, and that is what we are going to use. The machine learning tasks we are going to perform will use this workflow. We are first going to download the data. After that, we explore, clean and preprocess the data. The cleaned and preprocessed data will be split into two, i.e., training and test sets. The training sets will be fed to the machine learning model initially, and this is to help the model to learn and identify patterns that can be used to make future predictions. After that, we feed the trained model with the test subsets, and then we evaluate the model based on the predictions it makes on the test sets. After that, we visualize the results and I will explain them. Now that you are set, let the predictions begin. We begin by downloading the data, and this is the page where we download the data. I am going to leave this link also in the description box so that you can use that to visit this page. So if you enter this page, you might come across this, and if you do, click on the accept all cookies. Click on it, and then you'll be given access to the page. So on the page, scroll down and then come to the right side here. Search for supplementary information, this one here. Once you find it, click on it, and then you'll be sent to another section. So on this section here, scroll down until you see this line here, additional file 2. Once you see it, click on it, and then you'll be asked to save the file. So let's save it. Notice the file name and the extension. This is an Excel file. I'm going to save it on my desktop. You can also save it in any appropriate path on your PC. So let's save it. So I have saved it. You can also download this data using the second approach here, where you scroll up here, come to this side, click on this arrow here, and then when you see the 2/2, you come here and click on download. Once you do, you have this region highlighted, so you click on the download this file here, and then you'll be asked to save it. So these are the two approaches you can use to download the data. Now that we have our data downloaded, let's go and check out the file. So this is the file, and it is an Excel file. So what we are going to do is to convert this file into a CSV format. So we need to first open it. So you can open it with any spreadsheet software, Microsoft Office, LibreOffice, WPS, or any spreadsheet software. So let's open the file. So once you open it, you have this interface. The file contains two sheets, which are here. So what we want to do is to highlight this sheet, the first one here, which is table S2. So click on it to highlight that sheet. After you are done with that, we will now save this sheet as a CSV file. So we are going to use the Save As option. Please locate that on your respective software. So mine is here, so I'll go to Save As. And then I'll save it. When I come here, I'll first select the format, which is here. I'll click on it and select CSV. And then when I come here, I'll give the file a new name. So let me give it a name here. I will say malaria underscore clinical data.csv. So this is the name I'll give it. So please use same. And then I'll save it on my desktop. So I save it. You might have this warning, but you can ignore it and then go to OK. So save it. Now the file has been saved. Let's check it out. So there is a file, and this is what we are going to use for the rest of the activity. So let's go back to the Python interface and continue from there. So on the Python interface, the first thing we do is to import our libraries. We are going to import some of them: pandas, numpy, matplotlib, and seaborn. So we import them. After we have imported them, we then read the data. So to read the data, we need to first set a path to the file, and then we read the data with pandas. So let's set a path. So we say data file equals, and I give the full path. So this is the path to the file. Please note that we are using the CSV file that we generated. So take note of that. So this is the path of the file. I run it and then I read it with pandas. So I'll say data frame equals pd.read CSV, and I indicate the data file. So I'll run it. Now I've read the file. So we have a data frame, and data frames in pandas comprise of rows and columns. Now that we are done with the reading, we now have to explore, clean, and preprocess the data. Now, the purpose of exploring the data is to obtain information, and sometimes the information we obtain will help us to determine the appropriate methods and models to use for the downstream analysis. And the information will help us to also clean the data and preprocess the data. So we start the exploration by getting the number of rows and columns in the data frame. So we say data frame.shape, and this will give us the number of rows and columns. So in our case, in this tutorial, the number of rows represents the samples, and here the columns represents the measurements and the malaria outcomes. So we have the features and the class. So this is how it is for this data. Aside this one, we can also find, or we can also get the first n rows in the data frame, where the n can be any number. So let's try with the first 5 rows. So we say data frame dot head. let's use n equals 5. So this will return the first 5 rows of the data frame. So let's run it. And this is the first 5. Please note, if you don't bring anything here, pandas by default will return the first 5 rows. If you're looking to get any number above 5, you need to specify it here. But let's leave it with this default and values here. So this is the first 5 rows. So we have the columns here and we have the rows here. So at least we have some information here. Now, note this particular values here, NaN. Whenever you see NaN in pandas, it means missing values. So take note of that. We are going to talk about missing values later in the tutorial, but now just know that we have some missing values here. We can also get the list of column names in pandas data frame. So to do that, we say data frame.columns, and this will return the column names for us here. So we have sample ID, concept given, up to IBC dist with %. So this is how we do it with this particular command. As part of the exploration, it is important we get information such as data types, missing values, and columns. We have already displayed the columns, so let's look at how we can get this information as well. So to do that, it's simple. We say dataframe.info, and this will return this information for us. Now, let's look at this line here. We have range index 2204 entries. This tells us the number of samples. We have 0 to 2206. These are indexes. Python starts counting from 0. So if you are to do a query for the columns using the indexes, then we start from 0, meaning that the first column has an index of 0, and the rest will follow up to the last column here, which is this one here. So that is why we have the index to be 0 to 2206. Let's look at the data type, D type. This tells us the data type for the entries in the respective columns. Objects here could also mean string. We also have float values here, and we have some of them down here. Let's come to non-null counts. Non-null counts will tell us if the columns have their entries complete. For sample ID, we have 2207 non-null, meaning that for sample ID, all the samples have their sample ID column filled or entered, so there are values there. The same for consent given. When we come down to BedNet, we see there's a change. We have 1676. So this indicates that for the BedNet column, only 1676 samples had their portions filled. And this means that the rest are missing values. Notice we had NaN in some of the columns when we did the first n rows. So this is how it is. We also have fever symptom 2206. So at a glance, we know that there are missing values here with some of them here. So let's move on. Now with this data, we are interested in some of the columns, and some of them we don't need for the machine learning work. So what we need is from clinical diagnosis column here, which is 16, up to the last column, which is 33. Therefore, we need to subset this data. So what we are going to do is to issue another command to extract the needed information for us. So we are going to do the subset, and we start from column 16 to the last column. Column 16, the 16 refers to what? The index here for clinical diagnosis. So let me show you how it's done. We say subset equals data frame.ilog, and we indicate all rows, and then we want from column 16 up to the end. This is it. So now we issue the command. So let's issue it. So now we have the subsets done. Let's check the shape. We have 2207, 18 columns. Formerly we had what? 34 columns, but because we don't need all of them, we are using some. This is what we are left with, 18 of them. So we take notes. Of course, we can also look at the info. So we say subsets.info to get information. So from here at a glance, we also see that there are missing values here. Look at this one here, 2204, 2205. So we have some of them here. And this information is very, very important because when you are storing the data, one of the things you should look out for is what? Missing values. The issue of missing value can affect the model's performance. So you make sure you handle it. So at this point, we can say there's missing value, and therefore we need to handle the situation. But at the same time, we also want to find out the level of missingness. For each column, how many entries are missing? That is what we are going to do here. So we say subsets.snull.sum. This will give us the total of missing values for each column. So this is how we do it. So when you see 0, it means that for that column, the entries are complete. We don't have any missing value. Notice this one here is null. We are looking for the sum for the missing values. Here we have 3, meaning that 3 entries had missing data. We have 2, 9, 32, and so on. So at least we now have an idea of the level of missingness. And so what we have to do next is to handle this issue of missing data. So what we are going to do next is to handle this issue of missing values. Now, to handle missing values, you can either perform imputation or you can remove rows and columns with missing values. So in this tutorial, we are going to remove all rows with missing values. So this is how we do it. We say subset.drop any, and we indicate in place equals true. The in place equals true here means that after we have dropped all the missing values, the current values should overwrite or should replace the old values for the subset data frame. So let's drop the rows. Now we have the rows dropped. So we can check the shape again. So we say subsets.shape, and we have it here, 215618. Formerly we had 2207, but then we have dropped some of the rows with missing values. So this is what we are left with. And so here, at least for this data set we are confident that all the entries are present. Let's issue another command again to check the columns. So we have the column names here, clinical diagnosis up to RBC death rate %. Please note that the clinical diagnosis column contains the malaria outcomes. So what we are going to do is to get those outcomes. We want just the categories or the types of outcomes here, more like a summary of it. And so what we are going to do is to get the different malaria outcomes. And in this tutorial, I'm going to use labels, classes, and malaria outcomes interchangeably. In machine learning, outcomes, we usually refer to them as labels or classes. So please take note of that. Now, there are a number of ways you can use to get the clinical diagnosis outcomes. So let me show you two approaches now. One of them is to issue this command subsets, and we indicate the column we want, and we say dot unique. So the dot unique here means that we will get the entries here, and then all duplicates will be removed. So let's run it and see what will be returned for us. This is what we have: severe malaria, uncomplicated malaria, non-malaria infection, and that is what we need. But then let's use the second approach, which I prefer to use because we are dealing with categorical data. So in the second approach, we use this command here, pd.categorical, and then we indicate the same query here, minus this one here. So we assign the operation to what? A variable, which is labels. And then I will print out the labels here. So I have it here. So when you use this command, you have the labels being printed, and you might see 3 dots here. This indicates that some entries were not printed out or displayed. And when we come down here, we have the length, the total entries, and here we have categories, 3, and then data type. That's objects. So this information gives you the summary or the number of categories. And when you come here, it displays them for you. Here, it also sorts the labels for you, which is also a good thing to do. So now we have the outcomes for this particular data set. Now let's look at the first n rows. We see subset.head. So now we have what? The first 5 rows displayed, and now the data looks a bit clean. It looks cleaner than it was before. So we have the clinical diagnosis, we have all these values here. And please note that the clinical diagnosis is the class or labels, and then the others here are measurements, or we say features or predictor variables. That is how we refer to them in machine learning. So please take notes. As part of the exploration, it is important we get the class distribution. Let's look at it here. Class distribution. This is important because this will let us know if our data is imbalanced or not. And then it will also inform the model we use in the subsequent tasks. So let's look at how we do this. We say subset, and we issue this query here again, clinical diagnosis. You can try with other columns as well. We say dot value count. So we use this to find the class distribution. So let's run it. Now we have the class distribution printed here for us. Non-malaria infection 96s, uncomplicated malaria 702, severe malaria 488. Now let's compare non-malaria infection to severe malaria. Look at the difference and you realize that it's more than 400. So in my opinion, I would say that there is imbalance in the data because of this range here, which is wide for me. And this information is also very important. But then it will also be much better if you're able to visualize this distribution, because this will help us to really appreciate and understand what is going on and even do the comparison easily. So how do we do this? What we are going to do next is to plot a bar chart to display the class distribution. That is what we are going to do next. So to plot the bar charts, we issue the same command again here. and then we add some additional info. We say dot plot dot bar, and then we run it. So once you run it, you are going to have this bar chart being displayed here for you. So using this, it becomes easier to compare the distributions, the classes. And now you know that this and this are imbalanced, because if you check their heights, the difference is wide. So it's better to sometimes do visualizations of the data. And that is what we are doing right now. We move on to the next activity. Now, if we want to understand our data, it is important we also perform some descriptive statistics. We need to do this on the data. So how do we do this? We say subsets.iloc. We indicate we want all the rows, and we want from the first column, from the second column, that is where the feature starts. So from the second column up to the end, and we say dot describe. We then do a transpose just to rearrange the output. And once we have it done here, we run it. So let's correct for this. We have, it's supposed to be S here, transpose. So we do it here, and then we now run it. So now we have the descriptive statistics also displayed nicely for us here. So on this table, we get the count for each column, the mean, standard deviation, minimum, 25th, 50th, and 75th percentile, and the maximum value. Now let's observe the minimum and maximum values for each column. For the ABC count, we have 0.5, 53.90. RBC count 0.5, 6.67. Look at these two and check the others, and we are going to realize that for each of the column here, the values are in different ranges. And when you have such a situation, it is problematic for the machine learning models. And so we are going to correct for this at a later stage where we do standardization. So let's move on to the next activity. So as part of exploring the data, we can also check correlation. So that we find out if some features are correlated or not. So to do that, we say subset.corr, subset.core, and we run it. So we are going to get this correlation matrix here, which gives for each pair of columns, we have the correlation values. But we are better off if we visualize this. So it will be easier for us to interpret and understand this particular one here if we visualize this table here. So what we are going to do next is to visualize the table. As the saying goes, a picture is worth 1,000 words, and it's going to be easier if we do this. So let's look at how we will do it. We are going to visualize the correlation matrix using Seaborn. And this is how we do it. We say sns.heatmap, and we get the correlation again. We indicate the color map, which is cool, warm. We have it here. So we run it. So we have the heat map generated for us. On the heat map, you will find a color scheme on the right side. So the color scheme will help you to map out the correlation coefficients. So when it moves to this side upwards, then we are dealing with high correlated features. When we come down, we are dealing with correlations that are low. So let me interpret this by explaining with this example here. Let's look at the RBC counts here, and let's look at neutrophils counts. So check where they are, and then you find the color here, which is approaching this region here. And so what we can say is that these two features are highly correlated, because when you check the values here, the correlation coefficient value here, it's moving this way, which is high. So these two have a high correlation. Let's look at something here as well. Check the IBC dist width percent and check the HB level, and you will see that the color here is within this region, and that means that they have low correlation. So this is how we can interpret the correlation matrix when we visualize it. So this is just one explanation of it. Depending on your question, you might want to do some additional interpretation, but those ones are for future videos. You should also note that you can use correlation to remove redundant features or features that you don't need before you do your machine learning tasks. We call this operation feature selection, where you try to identify and select relevant features and use them for the machine learning work. But of course, in this tutorial, we are not going to do feature selection, but you just need to know that using correlation, you can remove unwanted features from your data. So this is how we do it for the correlation as well. So now we move on to the next phase, and that is data preprocessing. Data preprocessing helps us to properly format our data so that we can feed it to the machine learning model. So we begin by first separating the labels from the features, because when we are feeding to the machine learning model, we specify the labels and the features separately. So let's separate them. So we assign the operations to different variables. So x here will be for the features. So we say s equals subset.ilog. We want the entire row. We want from second column up to the end. Then we also issue for the class. We say subset.ilog entire row first column. So we run them. So please note that x for the features or measurements, y for the class or labels or malaria outcomes. So we run it. So we have the operation done. So let's check out the shape. We see x.shape, and we have it here 215670. Notice the subset data frame had what? 18 columns, but because we are separating, the features will have 17 columns. Let's do for the y. We see y.shape. That gives us 2156, and the column is just 1. So this is how we do it for the separation. Let's move on to the next activity. So the next activity is to encode the labels. We have to do encoding because it is required by scikit-learn to encode labels when performing supervised learning. And of course, what we are doing is supervised learning because for the samples we also have their corresponding outputs or outcomes. So this is a supervised learning problem. And we are going to use scikit-learn to do this. We are going to use the label encoder in scikit-learn. So let's import it. We say from sklearn.preprocessing import label encoder. We then create an instance. We say label encoder equals label encoder. We then feed it with the labels. We say label encoder dot fit y. So this here will give the labels to the encoder, and then the encoder will now generate the encodings. We then assign the encodings or map them to their classes. So we say y encoded equals label encoder dot transform y. So we run this. Now encoding has been done. So let's check out the values. Let's look at the first 5 values. So we see y encoded first 5. So this is the encoding. Let's look at the original values, which is y05. So we have it here. But then how do we know that the encodings have been assigned to a particular class? First of all, encoding will assign unique integer values to each of the classes or labels. That is what the encoding does. So we can infer or find out the mapping that has been done for each class or category. So let's get the class list from the encoder. We say classes equals label encoder dot classes, and then we print it. So this will return the classes for us. Here, the encoder sorts them as well. So what we have here, we can determine the encodings using the indexes. Non-malaria infection has an index of 0. Severe malaria 1. Uncomplicated malaria is 2. So whenever you see 0, it maps to non-malaria infection. 1 is for severe. 2, uncomplicated malaria. And that is why when we came here, the encodings were what? 1 for the first 5. And the original Y values, also the first 5 had what? Severe malaria. So at least here, we are able to infer that severe malaria has been encoded and assigned the value of 1. So that's how we do it for the encoding. So from here onwards, it is the encodings that we are going to use for the classification task. So what we are going to do next is to split the data into training and test subsets. The training subsets will be fed to the machine learning model, and this is to help the model to learn and identify patterns. And then after training, we feed the model with the test datasets. We are going to use a ratio of 80-20, meaning 80% of the data will be for training and 20% will be for tests. Please note that the split ratio here, before you select the ratio, you need to consider a number of factors, such as the data size, data variability, and others. Then you can use that to determine the appropriate split ratio. But for this tutorial, we are using 80-20. So please take note of that. And to split, we are going to use the train test splits model in scikit-learn. So let's import it. We say from sklearn.model selection import train test splits. We then proceed with the splitting. The splitting will return 4 values. So we assign those values to their respective variables. So we say xtrain, xtest, ytrain, ytest equals train test split. And we feed it with what the x values and the y encoded. And we specify the test size, which is 0.2. So now we run it. Now the splitting has been done, so let's check the shape. So xtrain.shape, ytrain.shape. They should have the same number of samples. So that is what we are checking. Let's do for tests. xtest.shape, ytest.shape. We also have the same number of samples. So we are good to go. So we'll move on to the next activity. And that is data standardization. Data standardization is to help us to scale our data so that the features have similar or the same scales, so that the values are within the same or similar range. We are doing this because machine learning models perform badly if the features have different scales. Notice when we had the descriptive statistics, let me scroll up here for you. We had this issue arising here where we had the values existing in different range. So we are going to correct for this by performing standardization. So let's go back and do it. So here what we are going to do is to scale the data so that the values are within the range of 0 and 1. So we are going to use the scikit-learn min-max scaler also for this. So let's import it. We say from sklearn.preprocessing import min-max scaler. Then we create an instance of it. We say min-max scaler equals min-max scaler. Then we scale the training and test sets. We do them separately and assign to different variables. So we say xtrain scaled equals min-max scaler.fit transform, and we say xtrain. We do same for tests. We say x test equals x test scaled equals min-max scaler.fit transform x tests. So we now run to scale them. Now scaling has been done. So let's quickly explore some of the scaled values and compare to the original. I will demonstrate with just the training set. So I say xtrain scaled. I want the first value. And then let me look at the original value, which is xtrain.ilog 0, 0. This is the original value, 13.8. So it is this value that has been scaled here. And the same treatment will be done for the other values as well, so that they are all within 0 and 1. Standardization also helps us to compare the features among themselves. And sometimes, if you don't standardize, then your model might even be biased, thinking that some of the features contribute higher than others. So we try to minimize this problem by performing standardization. Now let's move on to the next phase. So in the next phase, we do the training of the model. So this is the training phase. So the training phase is supposed to help the model to learn and identify patterns from the data. And so we are going to feed this model with the training subsets. I will demonstrate this activity using the random forest classifier. And please note that if you are performing a machine learning task, you should be able to justify why you are using a particular classifier. In this case, I am using random forest classifier because I am dealing with some multiclass data. Multiclass data is data with more than 2 outcomes. If it's 2, we have binary, but if it's 3 or more, it's multiclass. And when we had the class outcomes, notice we had 3 of them: non-malaria, severe malaria, uncomplicated malaria. So that is what we are doing now. So random forest is suitable for multiclass data. I repeat that again. I am going to use scikit-learn for this exercise. So from the scikit-learn package, I'll import the random forest classifier. So I say from sklearn.ensemble import random forest classifier. I then create an instance, so I say clf equals random forest classifier. I leave it with the default settings. Then I say clf.fit, and I feed it with the what skill data, x train skilled, and the y train. So we run it. So now training is complete. So let's move on to the next phase. And that is the testing phase. So in the testing phase, we let the model do the predictions on the test datasets, and then we evaluate the performance of the model. So let's first feed the data, that is the test sets, to the model, the trained model, and then we look at the predictions. So we assign the predictions that is going to be made to a variable. We say y_pred. That is y predicted. And we say model.predicts. In this case, we name the model CLF. So we say CLF.predicts. And we feed it with what? The test sets. So X tests skilled. Here, we don't add the y values because we want the model to do its own prediction. So we run it. Now predictions has been done. So let's check some of the values. Let's look at, let's say, the first 3. So we say y_pred 03. And these are the predictions. Let's look at the original values. These are the predicted values. Let's look at the original y values. That one is y test. These are the original values. When we compare, look at this and this. The predictions were the same as the original or the true y values. But when we come to this sample here, instead of 1, the model predicted 0. And so here we can see that there is a misclassification here. Notice that what is being predicted are values. So why do we have values being predicted instead of the names for the classes? Remember we did encoding. And so that is why the model is predicting the encodings for us. So we can map out the actual classes. And so to do that, we can refer back to the variable classes that we created. This one here, when we were doing the encoding. So let's print it and then look at the classes here. So from here, you can infer which of these encodings here map to a particular class using the indexing 0, 1, 2. So what we have here is 1, indicating that it maps to severe malaria. And so here, the actual or the true values is what? Severe malaria. But the model predicted what? Non-malaria infection here, which is 0. So that is the misclassification here. But these two were predicted correctly. What we've done so far is to compare just a few of the samples. So in the next phase, we are going to compare all the predictions and make some statements. So we move on to the evaluation phase. It is important that we assess the performance of the model, and we do that by comparing the predictions the model made to the actual or the true values. And that is why we are going to do the evaluation here. There are a number of metrics available to help us evaluate the model. And please note that your choice of metrics should be based on a number of factors, which include sample size, data imbalance, and others. So once you have considered these factors, you'll be able to select appropriate evaluation metrics. In this tutorial, I will use the following metrics: accuracy, F1 score, recall, precision, and confusion metrics. So let's begin. We first need to import them. We are going to use scikit for this as well. So let's import the metrics. So we say from sklen.metrics import balance accuracy score, F1 score, precision score, recall, and we also import the plot confusion matrix because we are going to visualize the confusion matrix. So notice here I have balance accuracy score, but I stated accuracy here. This is because the data set I'm using is imbalance. We got that from the class distribution. And scikit has a separate function that considers data imbalance when calculating for the accuracy. And that is the balanced accuracy score. So that is why I have this here. So what we are going to do is to begin the evaluation using the balance accuracy score. So to compute it, we say balance accuracy. We are assigning the operation to a variable. So we say balance accuracy equals balance accuracy score. And we feed it with the true values first, which is what y tests. Then we add the predicted y values. Now, sometimes the scores returned will be decimal places. Therefore, I would like to round the value to 2 decimal places. And I'll use the round function in Python to help me do that. So I'll say balance accuracy equals round. and I indicate the value here, balance accuracy, and I specify the number of decimal places, which is 2. I'll then print it as well. So I say balance accuracy, and then I print it. I specify the variable name so that anyone also watching will know that that particular value refers to balance accuracy. So let's compute this. So this is what we have, 0.73. That is for the balance accuracy score. So here I will say that the model performance is average in my opinion. But of course, we are not performing the same task as what was done in the original paper. And so the result we are getting here is not surprising. We are only doing some tutorial here, so at least we know how to evaluate the model performance. That is what it matters here. Let's move on to the next one, which is F1 score. So this is F1 score, and it gives us 0.7, which in my opinion is also average. But let's take a look at this parameter here. I am using average equals weighted. This is because scikit-learn from the documentation says that this parameter here accounts for data imbalance. And again, this is why it is important to explore the data, because from the exploration, we got to know that the data was imbalanced, and that is what informed the choice of this parameter here. Let's move on to the next score, and that is precision. So we run it. This gives us 0.74. Let's look at the next one, which is recall. And this gives us 0.73. Again, I'm using average equals weighted because the data is imbalanced. Let's look at the last performance metric, which is confusion matrix. So with the confusion matrix, we are going to visualize it. So this is the command I will use. So I run it, and I have the matrix generated here. So let's quickly look at the interpretation. With the confusion matrix, we have the true labels here, the predicted labels, and we have this color scheme here that maps to certain values in the cells here. Let's take a look at this one, for example. Look at non-malaria infection. This is a true label. This is the predicted label. So this value here means that 174 samples that were originally labeled as non-malaria infections were also predicted to be non-malaria infections by the model, and that is why we have 174 here. So this is a high number. That's majority of those original non-malaria infections were classified the same as the model, and that is why we have this number here as well. So this tells us that at least the model performed well when predicting non-malaria infection. But of course, we had some of them here which were supposed to be non-malaria infections, but the model predicted them to belong to different classes. We had 6 of them being predicted as severe malaria, and 10 of them being predicted as uncomplicated malaria. Now, there are a number of situations, or there are a number of reasons why models can behave this way, or why we can have misclassifications. One of them is that the data was mislabeled. If you are collecting data, there's that human factor, and so probably there was a mistake somewhere, and it resulted in the mislabeling of the data, and that is why we had this situation occur. It could also be due to outliers, but in this tutorial we did not correct or we did not handle outliers. It could also be that that particular data was labeled as non-malaria infection, so right, but the patterns there is similar to the other classes, and that is why the model classified them as such. But the most important thing and the good news is that majority of them were classified correctly. When we check severe malaria, it's a similar observation. Majority of them were classified correctly. When we come to uncomplicated malaria, this is interesting. Here we have 53 of the uncomplicated malaria cases being predicted correctly, but then majority of them had misclassifications. We had 69 of them being predicted as non-malaria infection, and we had 23 of them being predicted as severe malaria. And so this year, the model did not perform well in terms of predicting uncomplicated malaria cases, and this could be due to a number of factors, some of which I've earlier mentioned. So, and this is how we do it. And this is a quick interpretation of how the confusion matrix can be used to evaluate models. So please take note of that. So this brings us to the end of the evaluation phase. And in the next slide here, I show a summary of the results. So the table here has the results for the 4 metrics we used. And we also have the confusion matrix plots being displayed here for us. And so what I would say is that the model that we had, that we built, the performance I would say is average. And we did not get the same results as what was reported in the paper because we did not perform the same activities as was done in the paper. And so this result here is not surprising. Nevertheless, we were able to reproduce this paper to some extent, which is good and a good experience for us so far as machine learning is concerned. So that's actually a good thing. And you should also know that the model we built here, we could have improved the performance using a number of strategies. And I'm going to cover these strategies in other videos, in future videos I'll be making. But for now, I'm going to list some of these strategies for you. One of the strategies is that we can use more data. If you have more data, it becomes easier for the model to learn and identify patterns and then make good and accurate predictions. The next strategy is to be able to handle missing data. And of course, in this tutorial, we handle the missing data by removing all samples that had missing values. You should also consider removing outliers because outliers might affect the model's performance. Another strategy you can use is to perform feature selection. Feature selection will help you to identify the most informative features and use them for the classification task. When performing machine learning work, you can also consider using multiple classifiers and then select the best performing ones. In addition, we could have used hyperparameter tuning. This is where we tweak the parameters in the model and then we select the best performing ones. You can also use k-fold cross-validation. K-fold cross-validation, when used, helps to reduce the issue of overfitting. And the last but not the least, we can also use ensemble methods. Ensemble methods work by using several classifiers, and sometimes the result you get is better than using the individual classifiers. So these are some of the strategies you can use to improve your machine learning model. And so this is where I bring my tutorial to an end. And I'm going to make the notebook that I'm using here available on GitHub so that you can download them. The link will be in the description box. So then I will say thanks for watching, happy coding, and see you in the next session. Goodbye.